Black holes might not be bottomless pits of destruction. For decades, science fiction has painted them as cosmic vacuum cleaners, sucking in everything towards a point of infinite density called a singularity. But what if that terrifying image is completely wrong? A new idea from the frontiers of physics, called the Fuzzball, suggests black holes are something entirely different. By the end of this, you will understand a theory that could solve one of the greatest paradoxes in science. We will explore how these objects might not destroy information but store it, and what happens to anything that falls in. Does our universe hide its most profound secrets inside these enigmatic objects? That central point of infinite density is the singularity. It is the mathematical heart of a black hole, a place where gravity is predicted to become so overwhelmingly powerful that it crushes all matter into a single point. Think of it as a cosmic dead end, a spot where the very fabric of the universe gives up. Our most trusted laws, Einstein's theory of general relativity, which so beautifully describes gravity and the curvature of space-time, simply stop working here. The equations produce infinities, a sure sign that our understanding has hit a wall. Space and time as we experience them cease to have any meaning. For a physicist, this is more than just strange. It is deeply unsatisfying. It is like a detective following a perfect trail of clues, only for that trail to vanish into a bottomless chasm. The singularity represents a fundamental failure of our knowledge, a glaring sign that a deeper truth is hiding just beyond our current grasp. This is where a radically different idea steps in to challenge our cosmic understanding. To escape the trap of the singularity, we need to look at the universe on its smallest possible scale. Enter string theory. Forget for a moment everything you know about tiny, solid dots of matter, the electrons and quarks that we call fundamental particles. String theory proposes a beautiful and elegant alternative. What if these particles are not points at all? Imagine instead that the most basic building blocks of everything in existence are unimaginably small, vibrating loops of energy. Think of them as the strings on a cosmic violin. Each string is so incredibly tiny that if you enlarged an atom to the size of our entire solar system, a single string would be no larger than a tree on Earth. Now the magic happens in the vibration. A violin string can vibrate in different ways to produce distinct musical notes from a low C to a high A. In exactly the same way, these fundamental cosmic strings vibrate at different frequencies and patterns. One specific vibration might correspond to an electron. A different, more complex vibration might create a quark. Another unique resonance could even produce the photon, the particle of light. In this stunning vision of reality, every force and every particle we have ever discovered, everything that makes up you, me, and the distant stars, is just a different melody played on these tiny, vibrating strings. It is a single, unified symphony underlying all of creation. This elegant idea does more than just redefine particles. It demands an expansion of the very stage upon which the universe performs. For the mathematics of these vibrating strings to work consistently, they cannot simply dance on the three-dimensional space and one-dimensional time we are familiar with. The equations require extra dimensions, tiny, curled-up realms existing at every point in space, dimensions far too small for us to ever perceive directly. It is a vast and hidden architecture to reality, one that provides the necessary room for the strings to perform their cosmic concert. So, if our most basic objects are not destructive points but harmonious, vibrating strings, what does that mean for the most destructive objects we know, black holes? The answer lies in reimagining their very cause. Einstein's masterpiece, General Relativity, paints a breathtaking picture of gravity as the curvature of space and time itself. It predicts the bending of starlight, the expansion of the cosmos, and the very existence of black holes with stunning accuracy. But this powerful theory harbors a profound secret. It is not the final word on our universe. As we follow its predictions inward toward the very heart of a black hole, its brilliance begins to flicker and fade. The equations that so elegantly describe the warping of space-time start to produce answers that are not just strange but physically impossible. They predict the collapse of all matter into a single point of infinite density, a singularity. The problem with infinity is that it is not a number you can calculate with. It is a sign that your mathematics has broken down. Think of it like using a road map to navigate a city. The map works perfectly until you try to drive your car directly into a single, infinitely small point on the paper. The map offers no guidance. It simply stops being useful. That is precisely what happens to general relativity at the singularity. The theory does not just fail to tell us what happens there. It screams that a new set of rules must take over. This is the driving force behind the quest for a theory of everything. A single framework that can describe all the forces of nature, from the immense pull of gravity to the quirky rules of the quantum world. The singularity is the ultimate dead end for our current understanding, a glaring billboard on the cosmic highway that reads, "Bridge out ahead." It is not a flaw in Einstein's work, but rather a signpost pointing toward a deeper, more complete layer of reality waiting to be discovered. This contradiction at the heart of a black hole sets the stage for a crisis that threatened to tear modern physics apart. It all began when Stephen Hawking made a startling prediction. He realized that black holes are not entirely black. Due to strange quantum effects happening right at the edge of their event horizons, they should slowly leak a faint mist of particles, a phenomenon we now call Hawking radiation. This process causes the black hole to gradually lose mass, shrinking over unimaginable eons until it presumably vanishes in a final puff of energy. This was a brilliant insight, but it came with a devastating consequence. Think of a black hole that has swallowed a star. That star was made of atoms, each with a specific history and configuration. It was a complex structure full of information. According to the bedrock principle of quantum mechanics, information can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, be recoverable. This is like burning a book. The paper turns to ash and smoke, seemingly erasing the words. But a hypothetical superintelligence could, in theory, collect every single ash particle and trace of smoke, reverse the chemical reactions, and reconstruct the exact original book. The information was always there, just in a different form. Hawking's calculation suggested something far more radical. When a black hole evaporates and disappears, it takes all that information with it. The unique history of everything that ever fell in, the star, any planets, any astronauts, is erased from the universe forever. The final burst of Hawking radiation, according to his work, would be completely random and featureless, containing no trace of what created the black hole in the first place. This is the infamous information paradox. On one side, you have general relativity, which says black holes trap everything forever, leading to a singularity. On the other, you have quantum mechanics, which says information must be preserved. Hawking's discovery showed that when you combine them, you get a direct conflict. It was as if the two most successful theories in all of physics were pointing at the same object and screaming completely different, incompatible truths. For decades, this paradox stood as an impassable wall, a glaring sign that our understanding of reality was fundamentally broken. The universe, it seems, abhors a paradox as much as it does a vacuum. This deep conflict demanded a radical solution, one that would come not from patching the old theories, but from a complete reinvention of the black hole's very nature. The answer emerged from the world of strings, a proposal so elegant it reimagines the monster from the inside out. This is the fuzzball. Forget the empty, dark void leading to a crushing singularity. The fuzzball theory proposes that a black hole is a vast, incredibly dense and tangled ball of cosmic strings. a single gigantic entity that fills the entire region from the center all the way out to the event horizon. There is no empty space inside. There is no point of infinite density. The entire black hole is a solid, though indescribably exotic, object made of the fundamental threads of reality, vibrating in an unimaginably complex symphony. Picture a ball of yarn, but one where every single fiber is a vibrating string of energy woven together in the most intricate pattern possible. This ball is the black hole. Its surface, the event horizon, is not a gateway to nothingness, but the actual physical boundary of this strange cosmic object. This single idea shatters the old image completely. The terrifying plunge into an infinite pit is replaced by a simple, if bizarre, fact. If you were to fall toward a fuzzball, you would not pass through a ghostly horizon into another realm. You would simply collide with its surface. The entire structure is a fuzzy, vibrating sphere of pure string energy, hence the name. This resolves the information paradox in one breathtaking stroke. There is no singularity to destroy information. Instead, every single bit of data about what fell into the black hole is not lost, but meticulously encoded in the specific, unique vibrational pattern of the strings that make up the fuzzball. The information is stored, much like the data on a hard drive is stored in the magnetic orientation of its particles. It is scrambled and incredibly difficult to read, but it is permanently and safely preserved within the very fabric of the object itself. The black hole is no longer a cosmic shredder, but the universe's most secure and compact library. This single change, the replacement of a void with a vibrating ball, solves the most glaring problem with black holes. The singularity simply vanishes. With no empty space inside the event horizon, there is no place for matter to collapse into an infinitely dense point. Instead of a mathematical dead end, the entire interior is a physical object, a dense and fuzzy ball of strings. The paradox of infinite gravity and broken physics is elegantly sidestepped. There is no longer a point where our equations fail because the fuzzball has a defined structure all the way through. It is a complete object, just like a planet or a star, albeit one governed by the bizarre rules of string theory. You can think of the difference like this. The old model of a black hole was like a magical trapdoor that opened into a bottomless pit, a place where the laws of the universe ceased to apply. The fuzzball, in contrast, is more like reaching the core of the Earth. It is a solid, albeit incredibly strange, endpoint. You hit a wall of pure, vibrating energy. This resolves the crisis at the heart of the black hole. Physics does not break down because there is no longer a singularity for it to break down at. The fuzzball provides a stable, finite object that our theories can actually describe, finally bringing the monstrous black hole back into the fold of understandable cosmic phenomena. So the information is never truly lost. It is simply woven into the most complex tapestry imaginable. This is the fuzzball's masterstroke. Remember Hawking's terrifying conclusion that a black hole's evaporation permanently erases information from the universe. The fuzzball rewrites this entire script. Since the black hole is not an empty pit but a physical object, its Hawking radiation does not emerge from a mysterious void. Instead, that faint glow of particles leaks directly from the fuzzball's own vibrant surface. Think of the fuzzball as a hot, complex object, much like a burning log. The log does not simply vanish into nothingness as it burns. It releases heat and light, and the specific pattern of that radiation is dictated by the log's unique internal structure, the arrangement of its fibers and resins. In the same way, the exact nature of the Hawking radiation coming from a fuzzball is not random. It is meticulously encoded by the specific, intricate vibrations of its trillions upon trillions of strings. Every piece of information about what fell in, every atom of a swallowed star, is imprinted on those vibrations. As the fuzzball slowly loses mass through radiation, it is not erasing data. It is essentially reading its own structure aloud, broadcasting the story of its creation back out into the cosmos, one particle at a time. The information is radiated away, preserved in the subtle correlations between the escaping particles. It would be an almost impossibly difficult task to piece that story back together from the faint Hawking glow, but the crucial point is that the information is there. Quantum mechanics, with its sacred rule that information must be conserved, emerges completely intact. The paradox simply dissolves. The black hole is not a cosmic criminal that destroys the evidence. It is a scribe faithfully translating a history of collapse into a whisper of radiation, ensuring that no chapter of the universe's story is ever truly lost. This new picture paints a very different kind of surface. Unlike the mathematical simplicity of a classic event horizon, which is imagined as an perfectly smooth and featureless one-way membrane, the boundary of a fuzzball is a realm of profound complexity. It is not a sharp, clean line in space. Instead, think of it as a transition zone, a turbulent and fuzzy interface that buzzes with quantum activity. If you could somehow magnify this surface to a scale we could perceive, it would not look like a still, dark sphere. It would appear as a seething, intricate tapestry woven from the very fabric of spacetime itself, a dynamic and structured chaos. This is not a passive wall you hit, but an active, vibrating boundary layer where the individual strings that compose the fuzzball express themselves. The smooth, empty space predicted by general relativity is replaced by this incredibly dense, structured object. There is no quiet emptiness on the other side, just the intricate, vibrating interior of the fuzzball itself. So what would happen if you approached this bizarre object? The journey toward a fuzzball would be far stranger than the classic plunge into nothingness. You would not experience the famous spaghettification in the same way, stretched into a stream of atoms by tidal forces, only to vanish into a singularity you never reach. Instead, as you crossed the threshold of where the event horizon was supposed to be, you would simply merge with the fuzzball's surface. Your own atoms, your own fundamental particles, would become part of the intricate vibrational pattern of the strings. Your information, the unique configuration that makes you, would be instantly and permanently woven into the fuzzball's complex structure, adding another layer to its cosmic story. You do not fall in, you become part of the ball. This resolves the paradox of the horizon by eliminating its most troubling feature, the idea of a point of no return that leads to a lawless void. The fuzzball has no such interior emptiness. Its entire volume is filled with substance, a substance that stores every secret it has ever absorbed. This deep connection between the fuzzball and information storage points to one of the most mind-bending ideas in all of physics. The way a fuzzball encodes everything it contains on its two-dimensional surface is a perfect, real-world example of the holographic principle. Think about the hologram on your credit card. It is a flat, two-dimensional piece of film, yet it projects a full, three-dimensional image that you can look around. The holographic principle suggests that our universe might work in a surprisingly similar way. The information needed to describe everything within a certain volume of space, all the stars, planets, and dust, might not be stored throughout that volume, but could be entirely encoded on its outer boundary, its surface. It is as if the three-dimensional world we experience is a projection, a hologram emanating from a two-dimensional surface we can never see. This sounds like pure science fiction, but the mathematics behind it is compelling. A black hole presents the ultimate test case for this idea. Its immense gravity creates a region of space from which nothing, not even light, can escape. According to the laws of thermodynamics, the maximum amount of information any region of space can possibly hold is directly proportional to the area of its boundary, not its volume. This was a revolutionary insight. For any other object, a planet or a star, you would expect its information content to be related to how much stuff is inside it, its volume. But for a black hole, the ultimate container, the limit is set by its surface area. The fuzzball is the physical embodiment of this principle. It is not a hollow sphere with a secret interior. It is a ball where the entire three-dimensional interior is, in a sense, an illusion. All the information about what fell in is not spread throughout its volume. It is meticulously written onto the complex, vibrating strings that make up its two-dimensional surface. The fuzzball does not just resemble a hologram. It is a hologram. The three-dimensional structure we perceive from the outside is a direct consequence of the quantum data dancing on its boundary. This resolves the information paradox with breathtaking elegance. When the fuzzball radiates, it is not leaking information from a hidden interior. It is simply reading from its own external surface, the cosmic equivalent of a projector slowly dimming. The holographic principle transforms the black hole from a paradoxical anomaly into the rule. It suggests that this might not be a special property of black holes, but a fundamental feature of our universe. The space you are sitting in right now, with all its apparent depth and volume, might itself be a holographic projection from a distant, two-dimensional surface at the edge of the cosmos. The fuzzball is our first concrete example of this profound cosmic architecture in action. This ability to store information as a physical structure leads us to a profound breakthrough in understanding black hole thermodynamics. For decades, physicists struggled with a strange question. If a black hole is just a simple, empty pit defined only by its mass and spin, as the classical model suggests, how can it have any internal disorder or what we call entropy? Entropy is a measure of the number of ways a system can be rearranged internally without changing its outward appearance. Think of a messy room and a clean room that look identical from the outside with the door closed. The messy room has higher entropy because the stuff inside can be arranged in a vast number of disorganized ways, while the clean room has very few arrangements. The classical black hole, with its smooth event horizon and empty interior, seemed to have only one possible internal state, implying zero entropy. This was a major puzzle because Jacob Bekenstein and Stephen Hawking famously proved that black holes must have an enormous amount of entropy, proportional to the area of their event horizon. The old model offered no way to account for this. Where was all this hidden complexity? The fuzzball provides the stunning answer. Each unique vibrational pattern of its strings represents a distinct microstate. A microstate is one specific, exact configuration of the entire system. For a fuzzball, this means one particular, precise arrangement of how all its trillions of strings are vibrating and tangled together. Now imagine a black hole of a specific mass. From the outside, it looks the same regardless of what fell in to create it. But on the inside, as a fuzzball, it could be in any one of a staggering number of possible microstates. One microstate might correspond to the black hole formed from a collapsed star. Another, completely different microstate might represent the same black hole formed from a giant cloud of gas, or even from a collection of 1,000 planets. The outside looks identical, but the internal vibrational story is unique for each history. The sheer number of ways to weave the strings together to create an object of that particular mass and size is astronomically large, but it is a finite, countable number. When physicists calculated the number of possible microstates for a fuzzball, the result was a triumph. The logarithm of that enormous number perfectly reproduces the exact Bekenstein-Hawking entropy formula. The fuzzball is not just a vague idea. It quantitatively accounts for the hidden complexity that we knew a black hole must possess. It gives us a way to literally count the possibilities, transforming the black hole from a featureless sinkhole into the most complex and information-rich object in the entire cosmos. But this elegant resolution did not go unchallenged. A new paradox emerged, one so fierce it threatened to set the event horizon itself on fire. This is the AMPS paradox, named for the physicists who proposed a startling thought experiment. They argued that to preserve the laws of quantum mechanics for an outside observer, an entirely different and terrifying phenomenon must occur. Anyone crossing the event horizon would not experience empty space. They would be instantly incinerated by a blazing wall of energy, a firewall. The logic was brutal. For the information to be preserved from the outside perspective, as Hawking radiation carries it away, the entanglement connections between particles just inside and just outside the horizon must be severed. The only way to sever these quantum links so abruptly is with an immense release of energy, creating a literal curtain of fire. The event horizon, once a silent gateway, becomes the end of the line in the most violent way imaginable. This firewall hypothesis presents a stark choice. Either quantum mechanics is wrong for the infalling observer, who expects to float peacefully through the horizon, or general relativity is wrong, and the horizon is not a smooth, uneventful place. It forces physics to pick a side, and both options seem to violate a fundamental principle. The Fuzzball theory, however, sidesteps this fiery dilemma entirely. It offers a third, more peaceful path. Remember, in the Fuzzball picture, there is no empty space inside a horizon to fall through. The entire concept of peacefully crossing a mathematical boundary is a fiction. The Fuzzball's surface is not a one-way door into a mysterious interior. It is the actual, physical end of space itself. If you were to approach it, you would not encounter a firewall because there is no separate inside for such a wall to protect. You simply reach the object's boundary and merge with it. The information paradox is resolved not by creating a destructive barrier, but by eliminating the paradoxical interior altogether. The Fuzzball does not need a firewall because its surface is the ultimate and final destination. The AMP's argument, which relies on the existence of two separate regions of space, simply does not apply. The universe, according to the Fuzzball, is not cruel enough to build a cosmic incinerator. It is simply structured in a way that avoids the need for one, weaving information into a tangible, physical form that brings a strange and profound peace to the edge of our understanding. Your ship's alarms fall silent as the last of your thrusters fails. The black hole's gravity, an invisible hand, now has complete control. You are falling not into darkness, but toward a faint, shimmering sphere that grows to fill your entire view. This is the Fuzzball surface, and it is nothing like the empty horizon of the old theories. There is no moment of silent, smooth passage. Instead, the universe seems to shudder. Space itself, which felt so smooth and continuous just moments before, begins to churn and ripple around you. It is like flying from a calm ocean into the heart of a hurricane, where the very fabric of reality is a seething, turbulent foam. The closer you get, the more you realize this is not a surface you can cross. It is a boundary where existence as you know it comes to an end. Your ship does not break through a membrane. It meets a wall of pure, vibrating energy. The impact is not an explosion of fire and debris, but something far more profound. The atoms of your ship, the very electrons and quarks that make up your body, do not crumple. They are unraveled. Each fundamental particle is not a solid dot, but a tiny, vibrating loop of string. And as you collide with the Fuzzball, your strings begin to resonate with the strings of the colossal object itself. It is a cosmic symphony absorbing a single, final note. Your unique vibrational pattern, the specific arrangement of energy that held the memory of your life, your thoughts, and your journey, is instantly and permanently woven into the Fuzzball's intricate tapestry. You do not die in a void. You become a new, complex harmony in the largest and most secure library in the universe. From the outside, an observer would see your ship's image redden and fade, frozen forever at the point of impact, your story now a permanent part of the object's shimmering, holographic surface. The terrifying plunge into nothingness is replaced by a final, instantaneous merger, where information is not destroyed but eternally preserved. The mathematical world that gives birth to Fuzzballs is a landscape of breathtaking beauty and profound abstraction. To understand how strings construct these objects, we must first venture deeper into the architecture of string theory itself. Recall those tiny, vibrating loops of energy. For their vibrations to produce the rich diversity of our universe, they cannot simply dance in the 3 dimensions we see. The mathematics demands extra, hidden dimensions, curled up into shapes so small they are undetectable to our most powerful instruments. The properties of these hidden shapes dictate the possible vibrational notes of the strings, and therefore the laws of physics and the types of particles that can exist in our world. This is where a crucial ingredient enters the stage, the D-brane. Think of a D-brane as a sort of membrane, a surface that can exist within these higher dimensional space. A string is not always a free floating loop. It can have its endpoints anchored to these D-branes, much like a puppet on a string is tethered to a puppeteer's control. These branes are not passive stages. They are dynamic objects that carry their own energy and can vibrate and interact. Now, imagine bringing a huge collection of these D-branes together, stacking them and binding them in a specific, intricate configuration. The mathematics shows that when you arrange a sufficient number of these branes in just the right way, the system they create begins to exhibit a remarkable property. It develops its own powerful gravitational field. It becomes so massive and dense that it would, in the old picture, form a black hole with an event horizon. But in the world of strings, there is no collapse. Instead, this entire complex structure of branes and the strings attached to them swells to a definite size, filling the entire volume out to where the event horizon was predicted to be. This is the fuzzball. It is not a ball of yarn in the ordinary sense, but a precise, stable, and gargantuan tangle of D-branes and the strings that connect them, a single, coherent object defined by its specific quantum state. The old singularity is replaced by this vibrant, horizon-filling entity. The magic lies in the numbers. Physicists can actually count the number of possible ways to arrange the branes and strings to create an object with a specific mass and charge. This number of possible configurations, or microstates, is astronomically large but finite. When they calculate the entropy from this counting, it matches the famous Bekenstein-Hawking formula perfectly. The equations do not point to a void. They describe a physical, structured object whose surface complexity accounts for everything a black hole was ever supposed to be. The fuzzball is not a vague speculation. It is a direct and elegant prediction that emerges when you take the mathematics of strings seriously, revealing a universe where even the most terrifying objects are built from the same harmonious, vibrating threads as everything else. This beautiful mathematical picture faces one monumental challenge. How do we know if any of this is real? The fuzzball theory, for all its elegance, must eventually face the cold, hard light of observational data. The core of the problem is the event horizon itself. From a vast distance, a fuzzball and a classic black hole would appear nearly identical. Both are dark, massive objects with a powerful gravitational pull. To distinguish them, we need to find a way to probe the very region where they differ most dramatically, that mysterious boundary. Fortunately, we are no longer completely blind. The dawn of gravitational wave astronomy and the first ever image of a black hole's shadow have given us entirely new senses for observing the cosmos. These tools might one day reveal the subtle fingerprints of a fuzzball. When two massive objects like black holes spiral together and merge, they shake the very fabric of space-time, sending out ripples known as gravitational waves. Observatories like LIGO and Virgo have now detected these waves from many such collisions. In the classical model, the final moments of the inspiral involved two incredibly smooth event horizons stretching and distorting before they finally merge into a larger, quivering black hole. But what if the objects were fuzzballs? Their surfaces are not perfectly smooth. They are complex, vibrating structures. This difference in texture could leave a tiny, yet potentially detectable, imprint on the gravitational wave signal. The final ring down, the phase where the new single object settles into its stable form, might have a different tone, a different set of vibrational frequencies, if it is a fuzzball shaking off its excess energy rather than a featureless horizon. Picking out this difference from the incredibly faint signals we receive would be like trying to identify a specific violin in a symphony orchestra from a recording made 1 billion miles away. It is a monumental task, but not an impossible one for future, more sensitive detectors. Another promising signature lies in the shadow of a black hole. The famous image from the Event Horizon Telescope shows a dark central region, the shadow, surrounded by a bright ring of light. This shadow is not the object itself, but the absence of light captured by its intense gravity. A classical black hole's shadow is predicted to be almost perfectly circular and dark, a consequence of the smooth, empty space just outside its event horizon. A fuzzball, however, has a physical surface that is buzzing with quantum activity. This could potentially create a different environment for the light and plasma whipping around it. Some models suggest that the shadow of a fuzzball might not be as perfectly dark or as perfectly circular. There could be a subtle, shimmering fringe around the edge, a faint glow or a slight asymmetry caused by the structured, turbulent surface of the object itself. We are at the very beginning of this new era of observation. Current telescopes and gravitational wave detectors do not yet have the resolution to see these minute details. But the next generation of instruments, perhaps a space-based gravitational wave observatory or a global network of radio telescopes using our moon as an antenna, could one day collect enough data to spot these tiny deviations. The quest is not to see the strings themselves, but to witness the consequences of their existence. It is a search for the cosmic whispers that would tell us the universe is not built on points of destruction, but on a foundation of vibrating threads, forever weaving the story of reality into the heart of its darkest objects. These hidden dimensions are the secret architects of reality, the reason a fuzzball can even exist. You cannot build such an intricate object with only the 3 dimensions we see. A vibrating string in our familiar space of length, width, and height has only a limited number of ways it can move. It is like a musician trying to compose a symphony with only 3 notes. The result would be simple, repetitive, and incapable of capturing the immense complexity of a black hole's information. The extra dimensions provide the missing notes on the cosmic scale. They are not vast, empty expanses you could travel through. Instead, they are curled up into shapes called Calabi-Yau manifolds, fantastically complex geometric forms that exist at every single point in our familiar space. Think of a garden hose. From a distance, it looks like a simple one-dimensional line. But if you get very close, you see its surface is actually a 2-dimensional cylinder curled up into a circle. The extra dimensions of string theory are like that, but with far more intricate shapes, offering a rich, hidden landscape at the tiniest possible scale. It is on this landscape that the strings perform their true magic. A string is not just a loop that vibrates. It can also wrap around these tiny, curled-up dimensions like an elastic band stretched around a microscopic hoop. This winding adds another layer of complexity. Now, each string has 2 ways to store energy, through its vibrational frequency and through the number of times it is wound around a hidden dimension. The number of ways to combine these vibrations and windings becomes astronomically large. This is the key. A fuzzball is not a random tangle. It is a specific, stable configuration where a colossal number of strings, with their endpoints tied to D-branes, have settled into a particular pattern of vibrations and windings within this higher dimensional architecture. The entire structure is held together by the strings pulling on the branes and on each other, creating a gravitational field so intense it would form a classic black hole. But instead, the object swells to fill the space, becoming a definite fuzzy sphere. Without these extra dimensions, the strings would be like actors with no stage, unable to perform the complex play that constructs a fuzzball. They are the essential, unseen framework that allows for the immense diversity of quantum states, transforming a destructive singularity into a vibrant, information-rich object. The universe, it seems, requires more room to hide its greatest secrets. This tangled ball of strings might be far more than a cosmic library. It could also be a gateway. The same string theory mathematics that builds a fuzzball can, under specific conditions, produce a structure that looks identical to a wormhole. This is a profound connection. We have long imagined wormholes as shortcuts through the universe, tunnels connecting distant points in space and time. Yet they were always considered separate from black holes, which were seen as dead ends. The fuzzball theory blurs this line into oblivion. Think of the fuzzball not as a solid ball, but as a dense, complex knot of cosmic threads. Now imagine that this knot is not tied off. Instead, the strings themselves could be threading through the higher dimensions, forming a bridge, a cosmic filament connecting our location to another point in the cosmos, or even to another universe entirely. From the outside, it still looks like a black hole, a dark sphere of immense gravity, but its interior structure is not an end, it is a passage. You would not collide with a surface and have your information stored. You would be pulled into the knot, your strings becoming part of the bridge itself, and potentially emerge somewhere else entirely. This redefines the very nature of these objects. A black hole is no longer just a hole, it is a potential door. The difference between a destructive singularity and a traversable wormhole might simply be a matter of the specific vibrational pattern of the strings that compose it. One specific quantum state creates a fuzzball that stores information. A different, equally valid state might create a fuzzball that is a tunnel. This suggests a universe where the most powerful objects are multipurpose, their ultimate nature written in the hidden language of vibrating strings. The terrifying pit becomes a potential portal, and the dream of cosmic travel finds a possible, if deeply theoretical, home in the heart of physics itself. For all its elegant solutions, the fuzzball proposal faces a wall of healthy scientific skepticism. Is this beautiful idea simply too good to be true? Many physicists argue that it might be. The most significant criticism is a practical one. Constructing a precise mathematical description of a fuzzball is incredibly difficult. Researchers have successfully built these models for certain idealized, simplified black holes, ones that are not rotating and carry specific types of charge. But the universe is not so neat and tidy. Real black holes spin, often at a significant fraction of the speed of light. This rotation introduces immense complexity into the equations. So far, no one has managed to construct a complete, rigorous fuzzball solution for a realistic, rotating black hole. Without this crucial piece, skeptics question whether the theory can ever truly describe the objects we actually observe out in the cosmos. It is like having a brilliant theory of flight that only works for a paper airplane, while a jumbo jet sits on the runway waiting for an explanation. If string theory is the fundamental framework of the universe, it must be able to build all the furniture, not just the simplest chair. This gap is a major hurdle, leaving the fuzzball feeling, for some, like an incomplete sketch of a masterpiece. The second, and perhaps more profound, criticism is the total absence of direct experimental proof. We have not yet seen a fuzzball, and we cannot yet run an experiment to confirm its existence. All the evidence is currently theoretical and mathematical. The potential observational signatures, like subtle changes in gravitational waves or the shadow of a black hole, remain just that, potential. Our current telescopes and detectors are not sensitive enough to spot the minuscule differences between a classic black hole's smooth horizon and a fuzzball's vibrating surface. This lack of empirical data places the fuzzball firmly in the realm of theoretical speculation. No matter how compelling its internal logic may be, science at its core is driven by experiment and observation. Until we can point to a piece of data and say, this is a fuzzball and not a singularity, the idea remains a powerful and elegant possibility, but not an established fact. It stands as a brilliant answer to a deep theoretical crisis, waiting for the universe itself to give its final verdict. This shift from geometry to quantum structure is the true legacy of the fuzzball. It fundamentally rewrites the research program for black hole physics. For decades, scientists approached these objects through the lens of classical general relativity, treating them as perfect geometric shapes in the fabric of space-time. The focus was on their mass, their spin, their smooth event horizons, and the warped space-time around them. It was a top-down view concerned with the large-scale architecture. The fuzzball paradigm turns this approach on its head. It insists that to truly understand a black hole, you cannot start with its smooth exterior. You must begin from the bottom up by counting. You must calculate the vast number of possible quantum microstates, the specific arrangements of strings and branes that could possibly assemble to create an object of that particular mass and charge. The black hole is not defined by a single, simple solution to Einstein's equations. It is defined by a staggering collection of individual quantum descriptions. The smooth geometry we perceive from afar is not the fundamental reality. It is an emergent illusion, an average over an almost infinite number of buzzing, vibrating possibilities. This moves the entire field from a classical, geometric description to a quantum, microstate-based one. The question is no longer just what a black hole looks like, but what it is made of and how many different ways it can be built. This microstate perspective gives black holes a new and critical role in the greatest quest in modern physics, the search for a theory of quantum gravity. For over a century, general relativity and quantum mechanics have been the two pillars of physics, yet they speak different languages and refuse to be merged. Black holes have always been the ultimate battleground where these two theories meet and clash violently, producing paradoxes like the information loss problem. The fuzzball, by providing a complete quantum description of a black hole that naturally incorporates gravity, offers a potential peace treaty. It shows us what a fully quantum gravitational object looks like. It is a concrete example, a template for how gravity and quantum mechanics can be woven together into a single, coherent fabric. By studying the fuzzball's properties, its entropy, its radiation, and its structure, physicists are not just learning about black holes. They are decoding the very rulebook of quantum gravity itself. Every calculation of a fuzzball microstate is a step toward answering the monumental question of how the universe operates at its most fundamental level. The black hole is no longer a paradox to be feared, but a teacher holding the key to the final, unified theory of everything. The monsters of science fiction have always been terrifyingly simple, bottomless pits of cosmic doom. But fuzzballs rewrite the script for storytellers. Imagine a blockbuster film where a brave spacecraft does not plunge into a dark vortex to be spaghettified and lost. Instead, it approaches a shimmering, turbulent sphere, a colossal object humming with latent energy. The drama shifts from certain destruction to a high-stakes first contact. Could we communicate with this thing? Could we decode the information vibrating within its surface? The black hole is no longer a villain. It becomes an enigmatic character, a silent guardian of the universe's oldest secrets. This transforms the entire narrative. A black hole could be the ultimate archaeological site, holding the complete history of a long-dead civilization within its intricate structure. A hero's quest might not be to escape the hole, but to carefully retrieve a single, precious piece of data from its vast storage, like finding one specific book in a library larger than a galaxy. The tension comes from the sheer, fragile complexity of the object, not from its mindless power. What if a malfunctioning starship threatened to crash into the fuzzball, not to be destroyed, but to violently overwrite its pristine, ancient data with its own chaotic final moments, erasing cosmic history forever? The stakes become about preservation, not survival. or consider a far future saga where humanity has learned to read the Fuzzball's holographic surface. These objects become natural supercomputers, their internal vibrations performing calculations of unimaginable complexity. A civilization might project its entire consciousness onto the strings of a fuzzball, living within a simulated reality built from pure, vibrating energy. The black hole becomes a temple, a digital afterlife, or the foundation for a transcendent new form of life. This is the power of the fuzzball idea. It takes a symbol of finality and transforms it into a symbol of infinite potential, turning the darkest corners of our universe into the most promising frontiers for the stories we have yet to tell. That century-long quest for a unified theory has often felt like a search for a ghost, a set of beautiful equations that remained frustratingly abstract. We knew the two pillars of physics, general relativity and quantum mechanics, had to be reconciled, but what would that reconciliation actually look like in the real world? What is the physical object that embodies quantum gravity? For decades, the answer was a mathematical phantom, a concept without a concrete form. The fuzzball changes that. It is not just another abstract proposal. It is one of the most promising and tangible realizations of a quantum gravitational object we have ever conceived. Think of it as the first physical model, a blueprint for what happens when gravity and quantum mechanics are forced to coexist. General relativity gives us the stage, the smooth, curved geometry of spacetime. Quantum mechanics gives us the actors, the particles and fields that dance upon it. But when the stage itself becomes so warped that it collapses into a black hole, the old script falls apart. The actors and the stage begin to interact in ways the old rules cannot describe. The fuzzball provides the new script. It shows us explicitly how the quantum actors, the strings, can themselves build a new stage, a new structure that does not collapse. The geometry of the black hole is not imposed from the top down by Einstein's equations. It emerges from the bottom up, from the collective behavior of trillions of quantum entities organizing themselves. This is the holy grail in practice. We no longer have to imagine how quantum gravity might work. With the fuzzball, we can calculate it. We can count the number of ways the strings can arrange themselves and find that it perfectly accounts for the black hole's famous entropy. We can see how information is stored not in a mysterious void, but in the precise vibrational states of a physical object. We can understand how Hawking radiation emerges not as a paradox, but as a natural process of this quantum structure slowly evaporating. The fuzzball is more than a solution to the black hole information paradox. It is a prototype. It is our first clear glimpse of a quantum gravitational object, a tangible example that the universe we live in is not fundamentally geometric, but fundamentally quantum, with everything, even the most terrifying depths of space, built from the same vibrant, information-rich threads. This same principle that tames the black hole's heart might also explain the universe's very first moment. We face a similar paradox at the beginning of time. The Big Bang theory points back to an initial state of infinite density and temperature, a cosmic singularity where all known laws of physics break down. It is the ultimate starting point and also the ultimate dead end for our understanding. But what if the universe never experienced that violent, nonsensical point? If a black hole's singularity can be replaced by a structured fuzzball, why not the Big Bang singularity as well? Some physicists speculate that the newborn cosmos was not a dimensionless point, but a dense, vibrant object remarkably similar to a fuzzball. Imagine the entire observable universe in its first fleeting instant, compressed not into a singularity, but into a primordial fuzzball, a hot, tangled ball of strings vibrating with unimaginable energy. This would replace a mathematical absurdity with a physical, structured beginning. There would be no moment of true infinity, no point where physics ceased to function. Instead, the universe would have a definite, albeit incredibly small and dense, initial size brimming with quantum information. the Big Bang would not be an explosion from a point, but the rapid expansion and cooling of this primordial fuzzball. Its complex internal vibrations would have dictated the initial conditions for everything that followed, potentially explaining the precise arrangement of galaxies we see today. The same quantum structure that stores information in a black hole could have imprinted the universe's first blueprint. This idea transforms the Big Bang from a mysterious, one-time event into a physical process, a phase transition where a fuzzball state unfolded to create the space and time we inhabit. The universe's greatest mystery, its origin, might find its answer in the same elegant physics that solves the riddle of its darkest objects. Behind every cosmic revolution stands a person staring at a chalkboard. The fuzzball theory did not emerge from the void. It was born from the decades-long struggle of brilliant minds determined to solve the information paradox. A central figure in this story is Samir Mather, a theoretical physicist at The Ohio State University. In the early 2000s, Mather was deeply immersed in the mathematics of string theory, specifically studying the properties of D-branes. He and his team were calculating what happens when you bring a large number of these branes together. The math was leading them to a stunning realization. This specific configuration of branes and strings did not create a black hole with a hidden singularity. It produced a single, giant, horizon-filling object, a specific quantum state with a definite, fuzzy structure. This was the foundational insight, the moment a vague possibility crystallized into a concrete proposal. Mather famously described this object as a fuzzball, a name that perfectly captured its essence, replacing the hard, mathematical boundary of an event horizon with something complex and textured. His work provided the first detailed, mathematical blueprint for how a black hole could be a physical object that stores information. The journey was not a solitary one. The world of string theory is a global, collaborative, and fiercely competitive arena. For years, other giants in the field, like Andrew Strominger, Kamran Voffer, and Juan Maldacena, had been laying the groundwork, exploring the holographic principle and the quantum nature of black hole entropy. Their calculations showed that the information capacity of a black hole was indeed proportional to its surface area, not its volume. This was a crucial clue, a signpost pointing toward a surface-based solution. The race was on to find the physical object that could explain this. Eureka moments in this field are rarely dramatic shouts in a lab. They are quiet, intense realizations after months of painstaking calculation. The sudden clarity that a complex equation is describing something real and tangible. For Mather, it was the moment the numbers aligned, showing that the entropy derived from counting string states matched the Bekenstein-Hawking formula perfectly. For others, it was seeing how the holographic principle could be physically realized in a stringy object. These physicists were not just solving an abstract puzzle. They were driven by a deep-seated belief that the universe must be logical and consistent at its core. The information paradox was an affront to that belief, a screaming inconsistency that kept them awake at night. Their collaboration took place in seminar rooms and through late-night email exchanges, sharing preprint papers and challenging each other's assumptions. The competition was equally intense, a race to be the first to publish the next breakthrough, to present the most elegant solution. This human drama of frustration, persistence, and occasional triumph is the engine of theoretical physics. It is a reminder that our most profound ideas about the cosmos are not handed down from on high. They are forged in the minds of individuals who dare to spend their lives staring into the abyss, not with fear, but with a stubborn conviction that even the darkest secrets of the universe can be brought into the light. The existence of fuzzballs would do more than just solve a black hole paradox. It would illuminate the deepest nature of reality itself. For decades, string theory has been a breathtaking but unproven mathematical symphony, a beautiful set of ideas with little direct connection to the world we can observe. The fuzzball changes that completely. If these vibrating spheres are what we have been calling black holes, then string theory is no longer just an elegant abstraction. It becomes the practical engineering manual for the most extreme objects in the cosmos. We would have direct physical evidence that the fundamental building blocks of the universe are not points but strings. Think of it like this: for centuries we believed matter was made of indivisible atoms. Then we discovered electrons and a nucleus, proving a deeper layer existed. The fuzzball would be a discovery of similar magnitude, but for the very fabric of space-time. It would show that the bizarre predictions of string theory, the extra dimensions and the vibrating loops, are not mathematical curiosities. They are the actual physical machinery operating in the heart of a black hole. This would be a monumental shift. The theory would move from a candidate for a theory of everything to the most viable framework we have for describing the quantum gravity that shapes our universe. Every black hole would become a cosmic beacon, broadcasting the message that we live in a stringy cosmos, a universe woven from the same vibrant threads that create stars, planets, and life itself. We began with a terrifying void, a singularity where physics itself broke down. That single point of infinite density was more than a cosmic oddity. It was a crisis, a glaring sign that our understanding of the universe was fundamentally incomplete. It created a paradox that pitted our two greatest theories against each other, threatening to tear the very fabric of physics apart. The journey from that chaotic dead end to the elegant fuzzball is one of the most profound shifts in modern science. We have replaced a destructive infinity with a vibrant physical object. We have traded a lawless pit for the universe's most secure library. This single, beautiful idea does not just patch a problem. It weaves a solution from the very threads of reality, resolving the information paradox, honoring quantum mechanics, and giving black holes a tangible structure we can finally understand. The monstrous black hole is transformed. It is no longer a cosmic shredder, but the most complex and information-rich object in existence, a holographic guardian of cosmic history. Its surface hums with the story of everything it has ever absorbed, a permanent record written in the language of vibrating strings. The universe is stranger than we can suppose. What other secrets is it hiding? Share your thoughts on these cosmic mysteries in the